Welcome to the last talk of the day. Thanks for your patience and thanks for still being here. So in this last talk of this kind of Beam session, I'm going to talk about some features related to efficiency and performance. And I'm going to talk about them with the point of view of the runner and how the Beam API allows the runner to make smart decisions during the execution. So you've seen this slide already. So to recap for the people who did not attend the previous two talks, Apache Beam is a unified programming model that is designed to provide efficient and portable data processing pipelines. And here I highlight the three keywords, which are unified, efficient, and portable. And this talk will focus on efficient. So how does the Beam project works? Well, the Apache Beam project has three main components. The first is the Beam programming model, which is a theoretical model of how how data processing pipelines can be specified. The second element is a set of SDKs for your favorite language that can take some program you write in this SDK and make it into a specification that is conformant to the Beam model. So it's a pipeline construction phase. And then the third element of the Beam project is a set of runners. And the runners are the interface to various execution engines. So currently, we have three main runners, Flink, Spark, and Google Cloud Dataflow. So the Apache Beam, the Beam model, the Beam programming model, is based on basically 7 main constructs. So I'm just going to go through very quickly. The fundamental one is the notion of a P collection. A P collection is a parallel collection of time-stamped elements. So the notion of time is essential, as Ken's presentation showed, that are in Windows. So every element of a P collection has a timestamp associated with it, whether it's in the batch pipeline or string pipeline, and is part of a window. And this P collection can be bounded or unbounded. Then there are sources and readers. So sources and readers in Beam are how the P collections are initially produced. Then we have pardoos, which are how P collections can be transformed, and the various group by keys that allow you to reorganize your P collections as you wish. We have next the side inputs, which have been mentioned for Flink in previous talks, but also so that are useful to materialize a P collection during a pipeline and feed it to a next execution stage. And we have windows and triggers, which I will not get into too much in this talk. So the key aspect of the Beam programming model is that these 7 constructs are enough to express a really wide variety of processing pipelines. And it can go from classic batch, where every element is part of a global window, and where the timestamp does not matter. You can have batch with fixed windows. You can have streaming. You can have streaming with speculative, streaming with retractions, coming soon, and streaming with sessions. All right. So this is the Beam model, and now you're familiar with it. So, but in this talk, I want to talk about real executions of pipelines so realistic workloads. And one key thing about if you've run pipelines in production on real systems is that these pipelines have some elements of variability. So if you have a streaming pipeline, you must probably have variable input. So depending on the time of day or the time zone in which you are, you have varied input. In batch pipeline, you have also this notion that each stage might have a different amount of data or a different amount of processing needed to complete it. So one fundamental thing that happens in most distributed processing systems is what we can call the curse of configuration, is that when you design your pipeline, you usually have to provision your resources to execute your pipeline. And you have this balance, which was explained in the scaling talk earlier today, of do you want to over-provision resources for your peak utilization, or do you want to under-provision on purpose, but then sacrificing your SLA? Because you're going to trade your resources for example, extra latency. And what every practitioner of big data system will tell you is that if you want to get one of these systems in production, you're going to spend a lot of effort fine-tuning every single parameter of your job so that you minimize your resources and get your SLA respected, right? But what's best is if you don't have to do it. What's best is a system that adapts, that will provision whatever is needed, will fine-tune its own parameters when it's needed to achieve the maximum efficiency. And that's what I'm going to talk about today. So this was an illustration in streaming, where we have varying load of, let's say, input messages. And here is an example of the same phenomenon of something that is varying at execution time. And this is the problem of stragglers. So if you've executed batch pipelines, you know how they are executed. There are sequences of stages, and some stages will wait for previous stages to execute before being started. And even if you do everything you can to make sure that the workload is evenly distributed among your workers, you're still going to observe something like this, where here I've represented each worker as the vertical axis and the time on the horizontal axis, and where we see some of the workers that take much longer time to finish what they have to do than some others, right? And those that take more time are called stragglers. And there are many reasons why we have stragglers in batch systems. One might be that the data is not evenly distributed. For example, if you're reading from files in a directory and you affect one file to each worker, maybe the files actually don't have the same size. And then you will see something like this. You can also have files that are exactly the same size, but for some data, your processing needs are much bigger, therefore it takes longer. Or finally, you can also, even if those things are equal, if you run on any infrastructure, you have environmental factors. Maybe your network has hiccup at some point. Maybe one machine is actually a virtual machine that is sharing the same CPU with something else. Anyway, so you get those variants. And what's annoying in batch is that since for every stage we get this phenomenon, it's cumulative since the stages are waiting for each other to complete. And so people have been trying to solve this problem for a long time. So there are many ways to kind of try to mitigate it, making sure that you split the files in equal sizes, for example. That's a simple one. Preemptively oversplit is also a mechanism. So if your data is split into too many tasks, or let's say many tasks, then there is more chance that they're going to balance out. And this second bullet is actually what is recommended in the documentation of systems like Spark. They will say, well, you should try to fine-tune, but we recommend that you set a number of tasks that is like 3 times the number of workers or something like this. There are also some strategies where you detect the slow workers, and then, for example, you kill it, or you restart it preemptively, or you start executing the same task on another worker just as a backup. There are like more elaborate strategy where you can sample or all this, but this last one I don't think has ever been implemented in a real system. So the problem of all these strategies is that they have measured costs, but they actually do not solve the problem in general, because at runtime, you always have something that comes up. You always will have variance. So with these two issues, like this idea that in streaming your system should adapt to your input, or in batch where your input, your data, and your processing among workers is necessarily not balanced, we get this idea that is fundamental to Cloud Dataflow and to Beam, is that no amount of tuning will actually solve your problem. And you can think of it as, even if for your job you finely tune to the perfect settings that guarantees maximum execution efficiency, right? But then the next day you have your next batch of data, and the data is different, and so it doesn't work anymore. Or maybe 1 month later, you're going to run out of memory because your data is slightly bigger and you didn't provision perfectly, right? So our philosophy, and that we want to promote, is that the system should be able to dynamically adapt and get out of bad situations rather than hope through heuristics that we avoid it, right? There's this saying, like, hope is not a strategy. It's especially true in distributed systems. So I'm going to illustrate this idea and how it translates into Beam concepts, right? So the Beam abstractions have this fundamental idea that they are meant to empower the runner to make the right choices, or to make the choices that are pertinent, that are relevant for their own system. So one example is the notion of a bundle. So P collections are the kind of main abstraction for data in Beam, and a P collection is a set of elements, right? And we have in the Beam model this notion of bundle. And what is a bundle? Well, it's a group of elements within a P collection that are going to be processed and committed together. And the thing is that the Beam model does not tell you, does not specify how big those bundles should be, because it's up to the runner to decide. And so it gives this flexibility to the runner to decide. And the API in Beam, if you implement a Pardue, if you don't care about bundling, you're just going to override the process element method. But if you care about bundling, you can do extra things in start bundle or finish bundle. And it gives this flexibility. And the runner will be able to make the right choice. So for example, if you have a streaming runner, you care about latency, you therefore will favor smaller bundles and pay the overhead of having very frequent commits. However, if you're doing batch execution, you can have large bundles and fewer large commits, right? So this is not like a new thing. This is Flink does batch and streaming the same way. We have a notion of buffer, or Flink experts can confirm. So, but that's how the API allows the runner to make the right decision. So another example is sources. So one way you can read from a source is in batch, for example, is to let the user decide how many ways it should be split into, right? And that's the strategy used in many systems today. In Beam, we want to allow this, but also to allow the runner to decide. And the way we do this is through the source API. So the source API, if you implement a source, you should implement those two methods, which are get estimated size and split into bundles. So to illustrate how they work, let me just explain. So when the runner will execute, the source, which is part of the Beam SDK, so it's not part of the runner. So let's say here an example, I'm trying to read from a bucket in Google Cloud Storage. I want to read every file in this directory. So the runner doesn't know anything about this, so it's going to ask the source, what is your size? And the source is going to say, well, I sample or I do whatever I need to do to get the size, as is 50 terabytes. Okay? Then the runner, empowered by this API, can do whatever it needs to decide what is the actual size in which it wants to split this source. So for example, it can take into account what is the current cluster utilization. Maybe I can only affect 3 workers to this job, so there's no point splitting it in thousands of small chunks. Maybe I just need 3 chunks. There can be other constraints that the runner can take into account, like if there are other concurrent stages that need to read. Okay? And all this allows the runner to make the right decision to optimize for its own efficiency. And then the source, once you give it the actual size, the source will call the split into bundles and then return the list of sources. And then the runner can, from this list of sources, can then distribute it to workers to start processing work. So let's now talk about the Straggler problem, how we use the same philosophy to solve it. So to illustrate the Straggler problem, I'm going to use this diagram. So in this diagram, I have the workers on the vertical axis. So here I have 6 workers. I have the time on the horizontal axis. Okay? And I represent in green the tasks that have been done, so completed by a given worker. And in yellow is the tasks that are still active as of a particular time, which I put with this pink or purple line, where I put now. And in yellow, well, faded yellow, I put what is the estimated remaining time for that task. Okay? So that's the kind of prediction of completion for that particular task. So as of now, here, you have 1 worker that is about to become idle. Okay? And the other workers are still busy working on something. But idleness is bad, right? Because it's waste of money. So what you want to do, and that's what we do for in the Cloud Dataflow runner, is we split the tasks. So we use the average estimated completion time and split the tasks so that these extra chunks are reaffected to the workers in order to not have idle time. Okay? So what does it give? It gives a few minutes later this situation, okay? And now the estimates of each task is slightly different because we have more data. Maybe the one task we thought would be completed fast is actually going to complete later. One task that we thought would complete in a long time is actually making very fast progress. But this is something that goes into this idea that the system will surprise you. So you cannot, your initial predictions will be wrong. So your system will need to adapt and update its own predictions. So a few minutes later, you do the same thing again, and you still have a prediction for your tasks that are still running, and you can do it again, okay? So that's how to solve the problem of stragglers using this notion of dynamic work rebalancing. So how does it work in the wild? Well, this is an example of a pipeline that is doing a simple kind of map and reduce style of job on the Google Cloud Dataflow. It's reading from Google Cloud Storage using 400 virtual machines. And we've disabled dynamic work rebalancing just to demonstrate the phenomenon. And what you see is that here, the input is completely uniform. Every worker is reading exactly the same amount of data and is doing the exact same work. And yet, because it's the public cloud, because who knows, there is a large variance. And the variance can come from reading your data is a bit slower than on some machine, writing the data is a bit slower, your processing is a bit slower because you're sharing the core, whatever. But if you enable dynamic work rebalancing, what you have is you can see that the tasks have been cut and they have been set back to the workers that were idle, and your idle time is way less. You save 5 minutes out of your 20 minutes, and this is more money for you, okay? So how does it, why is this important? Well, one thing that is crucial to understand why dynamic work rebalancing is important is that it enables autoscaling in batch. If you don't have dynamic work rebalancing, you cannot have effective autoscaling in batch. Why is that? Well, here is an example. So you start a pipeline based on the size. So this is using autoscaling in the Google Cloud Dataflow service. So you start a pipeline, you don't set the number of workers. You let the runner decide, okay? The runner will look at the input size, say, well, I need maybe 80 workers, okay? And that's what you do here. You start there. But then maybe your processing is a bit slower than what the amount of data would suggest. So you upsize. And then it's even more slower than what you thought. So you keep upsizing, okay? And what's interesting is that initially, in how many tasks did we split the initial input? Well, maybe we split in like 160 or maybe 240 tasks, so that there is like 3 per workers, something like this. But that's definitely not enough as soon as we reach, I don't know, 1,000 workers, right? So dynamic work rebalancing is the only way you will be able to, when you bring up new workers, to keep them busy during the execution, okay? So this is a real pipeline. And you can see the vertical lines on this kind of blurry picture. The vertical lines are the points where we do the dynamic work rebalancing, where we split the tasks. So it marks the time where we generate new tasks to keep the new workers busy. So how is this linked to the Apache Beam API? Well, both for autoscaling and for dynamic work rebalancing, you need to have a way in the API for the runner to get the information to make the right decision, okay? And there are two ways to know about how much your pipeline is making progress for bounded or for unbounded sources. One way for bounded is to have this method, which is getFractionConsumed, which the runner can query to know from a source how much, what's your percentage done for this task. And for unbounded, well, you're never complete, but one thing to know to find out if you're struggling with your size of, like, input size, is to look at the backlog, right? So we have in the unbounded source API this method get backlog bytes, which returns how many bytes have been accumulated as a backlog from the reader. So this is implemented for like the PubSub reader and the Kafka source in Beam. And those can inform the runners, say, well, now I'm accumulating too much in the backlog, so it's time to upscale. Okay? And these are part of the Beam API, and any runner can just call them and do what it has to do to upscale, for example. And for splitting, to do the dynamic work rebalancing, it's also part of the source API. There is one, the main method is called split at fraction. So every source has the possibility to implement this method, and it empowers the runner to suggest a fraction at which to split. So let's say split at fraction 0.5 will tell the runner, will tell the source, well, give me back 50% of your task. And then the source is given back to the runner can do whatever it needs to assign it to a new worker, and it works. There is an interesting final API that is actually needed as well. So some sources, let's say your pipeline is processing video files, or let's say video files, it's doing encoding or something. Once you have one file, one video file, you cannot split it because you want to encode the whole thing into one result, right? So, but you still want to be able for one worker to work on multiple video files because you don't want to have the overhead of one task per file. So we have this method that allows to tell the runner how much parallelism is left in my source. And this tells the runner, okay, if my parallelism is only 100, there's no need to bring any new worker because if I bring a new worker, this new worker will never get work, even with dynamic work rebalancing, okay? So the get parallelism remaining is the method for which that allows autoscaling to scale up and finds the actual limit in the parallelism of your data without you having to specify it. Oh, Ken, I need your password. Sorry. Run.
You're going to say it. 1, 2, 3, 4, 5.
I'll do a dance. Okay, so that's how all these nice features are enabled by the API. Okay, so that was actually my almost last slide. So to just strengthen this last sentence again about what is Apache Beam. Apache Beam is a unified programming model designed to provide efficient and portable data processing pipeline. You write your pipeline once, you write your transforms once, and then you can apply them in batch, you can apply them in streaming, you can run them on Spark, you can run them on Flink, You can run them on the managed Google Cloud Dataflow service. But as a user, you have to write it only once. And it's designed to provide efficient execution through all these API that are implemented for sources and sinks. And this is, we think, is the way forward for big data processing system. So if you want to know more, there are a couple of blog posts that you can check out. And please join us in the Apache Beam community. Thank you. OK, there are a few questions. There's a question in the back.
Yeah. Thanks for this talk. I was wondering, the dynamic work rebalancing based on splitting, I can see how you can implement that for sources, but let's say you have longer pipelines doing multiple steps and so on. Is there a way you can do this for later stages of that pipeline as well? I could imagine it to be extremely valuable there.
Yes, you can. So for example, in this here, your pipeline has an initial source on the left where it's reading from Google Cloud storage. Then it's doing a group by key. So it's actually writing to shuffle, and then reading from shuffle, which is a source that you haven't specified in your pipeline. It's the kind of intermediate representation that the runner uses. Does it answer your question? So
it does to some extent. If I'm allowed to ask a follow-up question directly?
Sure.
OK.
We have a bit of time.
I can see how that kind of works for batch. So let's assume you're writing to shuffle, and I don't know, you ordered so that you can actually divide the output into certain key groups and kind of lazily split how many key groups go to what operator or so. But I can see how that works very well at a blocking boundary. Let's say you have a continuously flowing pipeline and you want to actually change it there. Doesn't it always require state migration? And isn't that then a point where it becomes kind of expensive, so it becomes a very tricky decision? Do we actually want to do that? Do you want to impose the overhead of migrating? If I want to split a certain bundle, or not a bundle is a different term here, but if I want to split the work that a certain worker started and actually give parts of it to another worker, don't I have to start migrating some amount of state and then take this into account? How much does that actually cost to migrate that state? Does it in the end actually pay off to migrate it, or?
That's an excellent question, and that's a question that the runner has to decide.
Okay.
Because the Apache Beam model just provides the input data, like the signals, and then the runner has to make his own trade-offs. Because for some runners, there might be some state to migrate. For some other runners, depending on their own implementation, there might not be any state to migrate. There might be some state to migrate for some sources, for not some sources. It's very runner dependent.
Okay.
And so the runner can make its own
actually,
decision.
I can see how that works on the managed Google Cloud service with mounted, remote storage and so on.
So that's one possible. Yeah, that helps.
Who can I throw the mic to?
There is some questions, or maybe start in the back.
Who's first?
For your other question about splitting, there is also a proposal in Apache Beam at the moment called splittable do-fun that would allow to split even inside of transform. So this, yeah, we're still improving the system.
Cool.
There's a question.
Who was next? There was someone there.
A bit of sport.
So in your example there, how do you specify when to create more, to allocate more nodes? Because you're speaking of saving of, it's going faster, it's spending only 5 minutes less, but you are running more nodes.
No, in this example, it's the same number of workers. So
yes. But I mean, at some point you decide to start more nodes to be able to get your job to be running faster, but it has a cost too, right?
Sorry, I don't understand. Because here we start with 400 workers, so 400 VMs on Google Cloud, and they stay alive all during the job.
Okay, but on the other example, you're just starting to...
So on this one?
Yeah, so...
Yeah, so there's a cost of starting new workers, yes. And it's, so it's an interesting trade-off to think about. It's like, in streaming, you have this trade-off of, do you want to keep your workers hot at the cost of extra latency, for example? Or do you prefer to keep your workers at, let's say, 30% CPU, but resulting in much lower latency, right? So there is always a bit of trade-off. And in batch, it's the same. You can, if you want to run on more workers, you can. And if those workers, like in here, get work immediately, then you pay only for what you use.
Yeah.
So it's fine. So in batch, on a public cloud where you don't have constraints on like provisioning much, it makes a lot of sense to upscale if you can, if you have enough work. In streaming, it's something that has very interesting balances.
Okay, thanks.
Give it another try.
This is dangerous.
We did talk about upscaling here. I'm just wondering, how do you downscale? Because that's also savings, right?
Yeah. So here I don't have an example with downsizing, but it works. So if, for example, the next stage, let's say there's another stage after this, the next stage is estimated to have very little data, then the system will decide, okay, let's kill 50% of the workers.
All right. Sorry, I have two related questions.
Sure.
Number one, the whole thing is sort of driven by the number of what is it called? Get parallel remaining or some remaining parallel?
No, so the
get parallelism remaining, right?
So this is a constraint. It's not all driven by this. This is an extra constraint to auto-scaling, so that if you know that your parallelism is limited, then this is a hard limit on what you should upscale to. So if you know that your input source cannot be split more than 100 times, then there's no point bringing up more than 100 workers.
Yeah, but how would I decide? I'm just wondering, I'm thinking out loud. How would I know what's the right value for get parallelism remaining and the number of bundles?
So it's a source. It's something that the source will can decide based on its own data. So for example, let's say you have a text source that is reading line by line. If you are at the last line, then your parallelism is 1. So you cannot split anymore. Your remaining parallelism is 1. If you're earlier, then maybe your parallelism will not get, you might get just an estimate based on how many lines you've read so far, and you can estimate how many lines there are remaining in your pipelines. But the source can provide either an estimate or an exact result in many cases. And if the estimate is not there, then the system will, the runner has also the capability of seeing that, oh, we've upsized, but the workers don't get work, so let's downsize.
Thanks.
I have an easy question. So what's the relationship between the abstractions of the source and the bundle? Because so is it like a source can produce multiple bundles, and what's the specification of? So
bundle is a bit overloaded in some cases. So we saw earlier there is this split into bundles method, which is not really well named, because those bundles are not the bundles that I was talking about earlier. So the runtime bundles, which are these ones, are something that the user can control a bit, but usually you would not, as a programmer, control them. You let the runner decide. For these bundles, those represent the different tasks, let's say.
All right.
Yeah.
And maybe one last question is, you showed how to split the sources for bounded data streams. What happens with unbounded? Is there an API for splitting those?
Yeah, there is, but the notion of dynamic splitting is not the same. There is no notion of Straggler or so a lot of these batch things do not apply.
Thank you.
Sure.
Anyone else?
Okay, there is one more.
Who? Stefan. I'm gonna.
A quick question: if you're working with unbounded sources and you're splitting them and you're moving, let's just say we have something like Kafka, right? And you started using 2 machines or so, and you had an ample number of partitions. So each machine was reading multiple partitions. And you would split and say, let's start moving some partitions to another machine. I think that's probably what it would boil down to at that point in time. So the point when you would want to move this, it's got to be sort of a consistency boundary, I guess. So
Yes.
how would you do this? Is this always at the boundary of the first thing called bundle on the first slide, the things that are like larger or smaller? Can it only occur between bundles, or can it also occur within a bundle?
So this is also something that the runner will decide. I can answer what the Cloud Dataflow runner would do. So it would basically checkpoint all its state, and then do whatever is needed to transfer states around, and then bring up the new worker and pick up exactly where it left off.
Cool. That sounds quite a lot like what Flink would also do.
Well, that's
amazing. Yeah.
Yes, because that's the, there's not 300 ways to
Exactly.
to do this, right? Okay, thank you very much.